Hi, I'm Joe Yu from Imperial College London. Today I'm going to present our work, SVD-NAS, Coupling Low-Rank Optimization and Neural Architecture Search. It is well known that CN models can be redundant in terms of the correlation, sparsity, and prediction of parameters. Therefore, CN compression brings the opportunity to help us balance the trade-off between accuracy versus flow parameter and latency for resource-constrained applications. Also, the compression only requires few number of training data, which is attractive because sometimes data cannot be easily shared because of the security, privacy, or intellectual property reasons. Low-rank estimation is one of the popular methods of CN compression. The task is to derive a sequence of light tensors from the pre-trained weights in order to reduce the number of parameters. Let's focus on the convolution layers. Since the weights of each convolution layer can be represented by this 4D tensor W, we need to identify a set of 2D tensors in order to approximate the original weights. We need to figure out the number of 2D tensors we'd like to use and also the shape of them. We also need to determine the type of operations we need in order to reconstruct the original weights from this 2D tensor. Some commonly used operations are listed here. If we look at the previous works on low-rank estimation, we found that they only considered a very limited number of design choices, and even for that small design space, their design flow is still not automated and requires extensive handcraft effort to hand-tune these decisions. Also, they favored the mean square error as a proxy of the network accuracy degradation, and we found this estimation is a very poor metric and will lead to suboptimal results. We reformulate the low-rank estimation into a NAS problem. We demonstrate that in order to identify the function of f and the shape of 2D tensors, the problem is equivalent to searching the design parameters of the building blocks shown at the right-hand side. We adopted the gradient descent-based NAS and constructed the layer 1 superblock. Inside each superblock, it includes all possible candidates of the design space. The convolution weights inside these candidates are inherited from the pre-trained weights. Therefore, the weights of these blue boxes are frozen during the searching process. Inside the superblock, we have the trainable sampling parameters, indicating the scores of each candidate. The sampling parameters are trained by minimizing the following loss function, which consider both entropy loss and performance cost. Once the searching ends, we then pick the candidate with a higher score inside the superblock. We then evaluate this design point under different scenarios of data availability. For post-training, which means no fine-tuning after searching, we find our method achieves evident accuracy improvement compared with previous work under the same compression ratios. And when we allow the fine-tuning on the full ImageNet training dataset, we find our method also outperforms the state-of-art method, which is ARDS shown in this table. Thank you for attention. For more information, you are welcome to read our paper and our code from these links.